Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. In the last episode, we explored the first and second law constraints underlying equilibrium among phases containing a single molecular species. This exploration led to the idea of Gibbs free energy as a metric of phase stability in systems of defined temperature and pressure, including a general prescription for formulating phase equilibrium problems with a single component. What I'd like to do in this episode is show you how we can extend this basic idea to two-component mixtures. This allows us to finally address some of the phase equilibria examples we've discussed since the beginning of the course, as well as introducing the idea of chemical potential, a key concept in the formulation of multi-component phase and reaction equilibria. So how do we extend the idea of Gibbs free energy to multiple components? To understand this, consider two phases, alpha and beta, at equilibrium at a common temperature T and pressure P. Imagine we transfer a differential amount of one species, D and I, from one system to the other, while leaving all the other species in place. This will cause a differential increase in the moles of species I in phase beta, and an equal and opposite reduction in the moles of I in phase alpha, while the moles of all the other species, J not equal to I, remain constant. When this happens, we need to consider two things. The first is that when we move species I from one phase to the other, it carries with it differential quantities of internal energy, volume, and other extensive properties. At the same time, other molecules in each phase must adjust to the introduction or removal of species I. According to the second law, for this transfer to occur spontaneously, the sum of all increases and decreases in free energy in both phases must be less than zero. Likewise, for the system to be in a state of equilibrium, in which case transfer of species I is not favored in one direction or the other, dg alpha must be equal and opposite to dg beta. So the question we need to address is what dg is as a function of d and I. Since temperature, pressure, and n sub j are being held constant during the movement of species I, the derivative we're interested in here is a partial derivative. So let's digress for a few moments on what partial derivatives are and how they are used in thermodynamics. Recall that if we have a function of a single variable, for example, temperature as a function of lateral position, x, the derivative of t with respect to x, dt dx, is itself a function, t prime of x. This function is equal to the local slope of t versus x at a particular value of x. This means that if we make a differential change dx in the value of x, we can calculate the differential change dt in the value of t by multiplying dx times t prime. Likewise, we can determine the total change in t over a finite interval, x0 to x1, by integrating t prime dx from x0 to x1. But imagine that instead of being a function of x only, t is a function of x, y, and z. Thus, to express differential changes in t, we need to consider how t varies in all three dimensions. Mathematically, this idea can be expressed as a total derivative, which is the sum of dx, dy, and dz multiplied by the partial derivatives of t with respect to each coordinate, holding the others fixed. In other words, we can still describe differential variations in t with respect to position, but not as a simple ratio. We need to consider variations in all relevant dimensions, which requires two or more partial derivatives. Applying this idea to Gibbs free energy, we can say that in general, g of a system will be a function of temperature, pressure, and the moles of each species present in the system. Thus, dg can be expressed as a sum of the partial derivatives with respect to Tp and the number of moles of each species. As you'll learn more about in Chem E 326, the first two of these partial derivatives are minus s and v, respectively. However, for now, let's focus on what happens when temperature and pressure are fixed, as well as the number of moles of all the other species, J not equal to I. In this case, we can ignore all partial derivatives save one, expressing dg as the partial derivative dg dni times dni. This partial derivative, known as the partial molar Gibbs free energy, has a particular significance in thermodynamics and thus gets its own symbol, represented here as a lowercase g sub I, with a bar over it. The partial molar Gibbs free energy is an example of what is known more generally as a partial molar property, defined as the partial derivative of an extensive property of a mixture with respect to the number of moles of one of the species in that mixture. To better understand the definition and significance of a partial molar property, let's compare it to a molar property of the same system. For example, imagine we have a mixture that has extensive property, capital B. We can define a molar property, lowercase b, which is the ratio of capital B to the total number of moles N in the system. We can also think of this ratio as the partial derivative of capital B with respect to N at fixed temperature and pressure. To better understand what this partial derivative means, consider a mixture of two species, red and blue, with a particular intensive value of lowercase b. Let's say that we have a system of a particular extensive size. We then add a small additional amount of the same mixture with the same intensive composition and properties. The total change in the value of extensive B will be dN times lowercase b. In other words, the molar property B only tells us how capital B scales with the size of the system, not on how capital B varies with the moles of one of the species. In contrast, partial molar B is defined as the partial derivative of extensive B with respect to the number of moles of one of the species in the system, while the others are held fixed. In thermodynamics, we often add subscripts to the partial derivative to indicate specifically which other variables are being held fixed. Returning to our mixture of red and blue with a particular extensive B, let's say we add a small differential amount of red only, dN red, to the system. This does two things at the same time. It expands the size of the system, but it also changes its composition, which changes its intensive properties a little bit when we add some of the red, selectively. Together, these changes result in a net change in extensive B of the system equal to dN red times the partial molar B with respect to the red species, B bar red. Unfortunately, textbooks and journal authors seldom agree on the symbols used for partial molar properties. Koretsky and some other authors use a capital letter with an overbar, tilde or caret, or other particle over it, and a subscript indicating the species being manipulated. I'm fine with the overbar, but personally don't like the use of a capital letter since it is inconsistent with the use of a lowercase letter for regular molar properties. Many chemists and physicists use a lowercase letter with no overbar, just a subscript indicating the species being manipulated, implying by the presence of a subscript that it is a partial molar property. The problem with this nomenclature in chemical engineering is that we often have problems where we need to distinguish partial molar B from molar B of pure I as a single phase substance, which we often write as B sub I. Thus, in these video lectures, I've adopted a hybrid notation involving a lowercase letter indicating a molar property and an overbar indicating a partial property. Since G equals H minus Ts, and thus is linearly related to H and S, the partial molar Gibbs free energy can be expressed as the partial molar enthalpy minus T times the partial molar entropy. This means that if we have separate expressions for H and S, we can separately calculate the partial molar H and S, and then add them up to get the partial molar Gibbs free energy. Also, in the case of a single component, changing the number of moles of the one species present cannot change the composition or intensive properties of the system. So the partial molar G, H, and S all reduce mathematically to the molar G, H, and S of that species as a pure phase. Okay, so returning to our phases alpha and beta, we can express the total change in G of the system as dNi times the difference in the partial molar Gibbs free energy between these two phases. Likewise, for alpha and beta to be in a stable equilibrium state and not pass a quantity of species I in one direction or the other, the partial molar Gibbs free energies of species I in both phases must be the same. Another way to think about the same problem is in terms of something called the reversible work, mu sub I. The reversible work is the work required to add additional amounts of species I to a particular phase. In general, this amount of work will depend on what variables are held fixed as we reversibly add species I. However, we can define a series of energy functions, including U, G, and the Helmholtz free energy, A, which are altered by the same amount, mu sub I, when species I is added to the system, with various binary combinations of S, V, T, or P held fixed. This reversible work is equal to the partial molar Gibbs free energy at fixed temperature and pressure. Thus, another way to say that species I is in equilibrium between two phases is that the reversible work of adding species I to each phase must be the same at equilibrium. This amount of reversible work is also called the chemical potential. The concept of chemical potential is an extremely useful and universal way to think about equilibrium phenomena, and has widespread applications in many branches of science and engineering. However, for our purposes here, we can think of the chemical potential equivalently to the partial molar Gibbs free energy, G sub I bar. These considerations lead to the following general conditions of equilibrium between two phases at thermal, mechanical, and chemical equilibrium. For any two phases alpha and beta, the temperature, pressure, and chemical potential of all species must be the same in both phases. For a single component at defined temperature and pressure, the chemical potential is the molar Gibbs free energy, as we discussed in the previous episode. What we're adding here is that for two or more species at defined temperature and pressure, the chemical potential of each species is the partial molar Gibbs free energy for that species. I'd like to now go through a series of examples where we use these generalized conditions of equilibrium, along with some additional concepts and assumptions, to derive equilibrium relationships in systems with relevance in chemical engineering. The first is a problem we considered extensively during the beginning of the quarter: vapor-liquid equilibrium in binary mixtures. Recall our examination of a px diagram for benzene-toluene mixtures at 80 degrees C, where we observed a two-phase region over a range of pressures and compositions. In this two-phase region, a system of a particular overall composition will split into a liquid, richer in toluene, and a gas, richer in benzene. What we'd like to do here is finally explain this behavior and come up with a predictive model for the location and curvature of the liquid and vapor saturation lines. To begin, we need a model for enthalpy and entropy. A common starting point for molecules having similar structure and properties is something called the ideal mixture approximation. To understand this approximation, consider a binary mixture of A and B. Imagine that the energetic interactions between A and B are similar to the interactions between A molecules in pure A and between B molecules in pure B. Let us also assume that the mixing of A and B is completely random. As I'll show you in a moment, these assumptions lead to the conclusion that the total enthalpy H of the mixture will just be a sum of the enthalpies of pure A and pure B before they are mixed. Entropy will be similar, but with an additional term for the configurational entropy of a random mixture. Note that the meaning of ideal in this context is quite different than for an ideal gas, where ideal means no molecular interactions. Here, in this context, ideal means the ability to linearly superpose the enthalpy and entropy contributions of the pure species, even when the interactions are quite strong, as they are in a liquid. Before going on, let's try to justify these expressions based on our assumptions in the two cases: an ideal gas and an incompressible liquid with like molecules. In the case of an ideal gas, it is relatively straightforward to understand the ideal mixture approximation. Imagine we have two unmixed gases A and B at temperature T and pressure P. To obtain the final mixture, we can take the two gases along a hypothetical path where we first lower their pressures isothermally to the partial pressure they will have in the mixture, and then combine them into the same space, preserving their partial pressures. Since the molecules are non-interacting and the mixing process is isothermal, the total internal energy of the gas mixture will just be the sum of the internal energies of the unmixed gases. Meanwhile, since both gases obey the ideal gas law, PV of the mixture equals nRT, which can be written as the sum of nRT for the two unmixed gases. Combining, the enthalpy of the mixture must be the sum of the enthalpies of the two unmixed gases. Because the molecules are non-interacting, we can also treat the entropy of the two gases separately. The molar entropy of both A and B increase when expanded to their final partial pressures. When we force the two gases to co-occupy the same overlapping space, their multiplicities are preserved. Adding and rearranging, we get a final result that S is the sum of the entropies of the original unexpanded gases plus a mixing term. For liquids, justification of the ideal mixture approximation is more subtle, since interactions in a liquid are quite strong. To understand what we might expect, consider a mixture of molecules which exhibit Lennard-Jones interactions. For molecules having similar types of interactions, we might expect the A-B interactions to obey some kind of average. In particular, sigma AB, which is nominally the sum of the molecular radii of the two interacting molecules, is expected to be the arithmetic average of sigma AA and sigma BB. Likewise, epsilon AB might be expected to behave the same way due to the intermediate distance established by A and B. Assuming these averages are correct, imagine what happens when we mix the two liquids. Before mixing, each molecule will be surrounded by some average number of nearest neighbors, lambda, with which they have the strongest interactions, which are on the order of epsilon in strength. Assuming the molecules are similar in shape and type of interactions, lambda is expected to be similar between the two substances. Thus, the potential energy contribution to the internal energy is expected to scale as the number of molecules times lambda times epsilon. If mixed randomly, the number of A and B molecules near each molecule will be proportional to the mole fraction of A versus B. Thus, the total potential energy associated with the A molecules will be proportional to the number of A molecules times lambda times a composition-weighted average of epsilon AA and epsilon AB. A similar argument holds for the B molecules. If we now substitute that epsilon AB is an arithmetic average of epsilon AA and epsilon BB, we find that U of the mixture ends up just as the sum of the internal energy of the unmixed components. Meanwhile, if we assume the molecules are close packed and incompressible, we expect the volume of the mixture to be the sum of the volumes of the unmixed liquids. Combining U and PV together for the mixture, we find that H of the mixture is the sum of the enthalpies of the two unmixed liquids, in agreement with the ideal mixture approximation. Note that although the final result is the same as for an ideal gas, the reason is totally different. In an ideal gas, there are no potential energy interactions. In a liquid, there are strong interactions, but because the molecules are similar, the replacement of AA and BB interactions with AB interactions results in a similar superposition of the internal energies. A similar situation holds for the entropy. Each component brings with it a certain amount of entropy to the mixture, determined by the ability of the molecules to move around in a dense liquid. On top of this, we must add the configurational entropy generated by mixing the species randomly. Recall we derived this expression for the configurational entropy on problem set 5 by considering the random mixing of A and B on a fixed lattice. In the case of a liquid, where molecules are closely packed together and space-filling, we might expect the same result, provided the mixture is totally random. Now that we have a model for how H and S of the mixture depend on composition, we can calculate the partial molar properties. In the case of an ideal mixture, taking the partial derivative of H with respect to Na yields the molar enthalpy of pure A. This is true of the liquid or gas. Since the molar enthalpies of a gas or incompressible liquid are only functions of temperature, so are the partial molar enthalpies. Taking the partial derivative of S with respect to Na is slightly more complicated, since the random mixing term contains Xa, which is a function of Na. Substituting, we can see that there are a total of 5 terms containing Na. Applying the chain rule, and then eliminating terms that sum to 0, we end up with the simple expression shown here. The partial molar entropy is the sum of the molar entropy of pure A minus R log Xa. For liquids, we expect the entropy of pure liquid A to be independent of pressure. Thus, the partial molar entropy will be a function of temperature and composition only. However, the entropy of pure A as a gas depends on both temperature and pressure. Adopting a pressure reference state of P0, we can express the entropy of pure A as the entropy at temperature T and pressure P0 minus R log of P over P0. Thus, the partial molar entropy of A in the gas depends on temperature, pressure, and composition. At equilibrium, the chemical potential of A in the gas and liquid must be equal. Re-expressing G bar as H bar minus Ts bar, and substituting the expressions we just derived from H and S, we get the equation shown here. Note that the quantities here and here correspond to the Gibbs free energy of the liquid and gas at temperature T and pressure P0. Collecting these terms together, we can identify this as the standard Gibbs free energy of vaporization at temperature T and pressure P0. Note that this term is not zero because it is defined at a standard pressure P0, not the saturation pressure at temperature T. In the limit of pure A, where XA equals 1, the pressure will be the saturation pressure of pure A. This allows us to express delta G0 vaporization as minus RT log P sat over P0. Substituting and then eliminating P0, we end up with a much simpler expression shown here. Repeating for species B, we get a similar result. Hopefully in this form you now recognize this as Raoult's law, a commonly used model for vapor-liquid equilibrium involving binary mixtures of like molecules. What does Raoult's law look like on a px diagram? This is easily answered by plotting P versus XA liquid and XA gas. For the liquid, we can say that the total pressure will be a sum of the partial pressures of A and B, which in turn are proportional to XA in the liquid, according to Raoult's law. Rearranging to isolate the intercept and slope, we get a straight line extending from PB sat to PA sat, as XA liquid goes from 0 to 1. This is the liquid saturation line. Meanwhile, if we again use Raoult's law to express XA liquid in terms of XA gas, we get the relationship shown here. Isolating pressure, we get a curved line extending from PB sat to PA sat as XA gas goes from 0 to 1. This is the saturation line for the gas. This analysis shows that Raoult's law, which results in the type of simple px diagram governing mixtures like benzene and toluene, is a manifestation of an ideal mixture, where A and B interactions in the liquid are similar to AA and BB interactions. As you'll see on the problem set, adding an unfavorable interaction changes this situation and leads predictably to non-ideal behavior, including the formation of an azeotrope. The remaining examples I'd like to show involve another important asymptotic limit of chemical potential, the case of a dilute liquid solution. Let's first cover this generally, and then we can dig into a couple of specific examples. By dilute solution, I mean a binary mixture in which one of the species, called the solvent, is in overwhelming abundance, and thus behaves much like it does as a pure liquid. Meanwhile, the other component, called the solute, is so dilute that individual molecules of the solute mostly interact with solvent molecules, not other solute molecules. In this limit, we expect the enthalpy of the mixture to equal the enthalpy of the solvent plus a term linearly proportional to the number of moles of the solute, Ni, that we add to the solvent. The constant of proportionality, Hi0, a molar property that is a function of temperature and pressure, represents both the enthalpy of the solute as a pure species, plus energetic interactions with the solvent when added to the mixture. The entropy is similar, but we also need to include a term representing the configurational entropy of the solute in the mixture. For a deeper justification of this from the standpoint of multiplicity, see episode B6, where I went through a specific example involving dilute protein molecules in solution. Taking the partial derivatives of H and S with respect to N sub I, and then substituting into the chemical potential, we get the expression shown here. For dilute solutions, the chemical potential will be a constant μI0 plus RT times the log of the solute concentration, Ci, divided by Ci0, where μI0 is the chemical potential at standard concentration of Ci0. Comparing this expression to the ones we derived previously for an ideal solution in the liquid or gas, we see a very similar dependence. In each case, we are describing chemical potential as a function of composition relative to some secondary reference state of composition. For ideal gases, the reference is usually some standard pressure, such as 1 atmosphere. For liquids, obeying the ideal mixture approximation, the reference is usually the pure species, where Xi equals 1. For dilute solutions, the standard concentration is usually chosen arbitrarily, but in some cases is set to a standard, such as 1 mole per kilogram of solvent. However, unlike the case with an ideal mixture, this expression is generally valid for any solute, provided the concentration remains very low. One important prediction of this behavior is something called Henry's law, which is often used to express the solubility of gases in liquids. For example, consider the problem of oxygen solubility in water. O2 is a non-polar molecule with very high volatility, so to first approximation, we might expect it to be insoluble in highly polar hydrogen bonding water. However, if O2 could not dissolve in water, aerobic life would not be possible. For example, consider a fish. How could it breathe if O2 was not soluble in H2O? The solubility of O2 in H2O determines many aspects of life on Earth. So let's try to assemble a model for this solubility based on the principles we've discussed so far. According to the general conditions of equilibrium, the chemical potential of O2 in the water and gas must be equal at equilibrium. Assuming the gas is ideal and that the O2 concentration in the water is small, we can re-express these chemical potentials relative to relevant secondary reference states in the gas and liquid phase. Substituting and solving for the O2 concentration in the liquid, we find that it will be proportional to the oxygen partial pressure of the gas times an exponential term containing the difference in chemical potential of O2 between the gas and liquid under standard conditions. This difference is called the standard Gibbs free energy of solvation. Collecting the terms not involving the PO2, we end up with Henry's law, which predicts a linear relationship between solute concentration and the gas phase partial pressure. On a graph, we expect the solubility to look something like this, with a dependence that becomes linear at low concentration, with a slope kh equal to the terms shown here. At 298 Kelvin, the standard free energy of solvation is about 16.5 kilojoules per mole, which means that solvation of O2 is quite unfavorable. However, the second law is a powerful motivator. The ability of the molecules to spread out in dilute solution counterbalances this unfavorable interaction under standard conditions of 1 mole per kilogram. We can see this by calculating the Henry's law constant. Substituting delta G0 in the expression above, we obtain a constant of 0.0013 moles per kilogram per bar. At 1 bar pressure, this concentration is within about an order of magnitude of the concentration in the air. So the fish actually have quite a bit of oxygen to breathe. Returning to the general question of dilute solutions, the other aspect of this asymptote is the chemical potential of the solvent. For example, the chemical potential of water plays an enormously important role in many aqueous phase chemical reactions, biological processes, or physical phenomena. Unlike the solute, which is dilute, the solvent is not dilute, so we can't assume it has negligible interactions with itself. So how do we go about predicting the chemical potential of a solvent? Well, it turns out that, much like mole fraction, the chemical potentials of species in solution are not all independent. So in a binary mixture, if we have a model for the chemical potential of one of the species, we can work out the chemical potentials of the other species, including the solvent. To understand this, consider a general multi-component system at defined temperature and pressure. Taking a total derivative of G, we can see that dG is the sum of mu I times dNi, since mu I is the partial molar Gibbs free energy. Integrating at constant composition, where mu I is fixed, we can also say that G is the sum of mu I times Ni. If we now take a total derivative with respect to all the variables, assuming nothing about how these variables vary with each other, we get the sum of mu I dNi plus the sum of Ni d mu I. Comparing to the expression above, and requiring both to be true at the same time, we require that 0 equals the sum of ni d mu I. Or by extension, 0 is the sum of xi d mu I. This general result is called the Gibbs-Duhem equation, which places a constraint on how the chemical potentials of various species in the system can vary with respect to each other. To see how this works, consider a binary mixture of a dilute solute A in a solvent. According to the Gibbs-Duhem equation, any changes in mu A must be accompanied by a change in the solvent chemical potential, with a ratio dependent on the concentration of the solute. Since the solute is dilute, we expect its chemical potential to vary as the log of Xa. Taking the derivative, substituting into the Gibbs-Duhem equation, and then integrating, we can see that the solvent chemical potential will scale as RT log of 1 minus Xa, plus a constant of integration. Recognizing that when Xa goes to 0, the chemical potential must equal the chemical potential of the pure solvent, we can solve for the constant of integration. The resulting expression shows that although the chemical potential of the solvent depends on other properties of the solvent through mu0, it does not depend on the identity of the solute, only on its concentration. This is known as a colligative property. One prominent example of a colligative property, and the final example of this episode, is freezing point depression. We've already discussed this effect in the context of the salt-water eutectic and the making of old-fashioned ice cream. Using the principles we just learned, let's try to predict some portions of the H2O NaCl phase diagram. In particular, consider a two-phase system containing pure solid ice in equilibrium with brine, a liquid solution containing H2O and NaCl. In order to develop a model for this system, let's assume the NaCl completely dissolves to form separate ions, Na plus and Cl minus, which we consider to be dilute. They are actually not very dilute, but let's assume so anyways to get a first-order approximation of what's going on. With this assumption, the chemical potentials of the two ions will be given by a standard chemical potential plus RT log of the concentration. However, due to the electroneutrality of the mixture, the concentrations of Na plus and Cl minus are not independent. They must be equal to the formula concentration of dissolved NaCl. This leads to the chemical potential of NaCl scaling as 2RT times the log of the salt concentration. Taking the derivative and then substituting into the Gibbs-Duhem equation, we get the expression shown here. Upon integration, this predicts that the chemical potential of H2O in the brine will be equal to the chemical potential of pure liquid water, plus a term related to the salt concentration. To understand freezing point depression, we must combine this composition dependence in the brine with expressions for the temperature dependence of the chemical potentials of pure solid and pure liquid H2O. In the case of the solid, we can do this by first expressing mu of ice as H minus Ts, and then imagining an isobaric hypothetical path from the melting point, T0, to temperature T. The resulting expressions, shown here, are the same as the ones we derived in episodes B4 and B8 for an incompressible substance at low pressure, assuming constant heat capacity. For pure liquid H2O, the procedure is similar, but we must also include the enthalpy and entropy of the phase change at T equals T0. Substituting into our previous expression for the H2O chemical potential in the brine and equating to the chemical potential in the ice, we can solve for XNaCl as a function of temperature. This results in the expression shown here. Note that as the temperature approaches the normal melting point, T0, the value of XNaCl goes to 0, corresponding to pure H2O. However, at temperatures below this, liquid brine can exist in stable equilibrium with solid ice for values of XNaCl which are greater than 0. A plot of this function is shown here, where I have substituted the weight fraction of NaCl in place of the mole fraction. As you can see, the saturation line behaves very similarly to the saturation line we saw on an H2O NaCl phase diagram. However, there are two important differences. The first is that there is no eutectic. This is because in our model we have not considered the equilibrium of NaCl in the brine with solid salt hydrate. If we did, it would predict an opposing salt saturation line that intersects the H2O saturation line at the eutectic. The second difference is that this model assumes dilute solution. Ions interact via Coulombic interactions, which are much longer range than van der Waals forces. So even at 10 weight% sodium chloride, the solution will not really obey the dilute solution approximation. This causes the model to underpredict the freezing point depression at the eutectic composition by a few degrees. However, the qualitative behavior is very similar to what we saw in the phase diagram. As we'll discuss in the next episode, the concept of chemical potential is broadly applicable to many problems in thermodynamics that go beyond phase equilibrium in binary mixtures, including reaction equilibria and multi-component mixtures. It also forms the foundation for the Lewis-Randall formulation of phase equilibria, which you'll study in much more depth in Chemie 326. However, in all these applications, the same basic principle applies. In order for a system to be at equilibrium, the temperature, pressure, and chemical potential of all species must be uniform throughout the system.